All right, so now that we know how to find the local and global maxima and minima of different functions using first and second derivatives, we can do some applied optimization problems. Okay, and so these come in lots of different flavors. So I'll just do a couple, and then hopefully you can get a sense of the process by which you would do one of these optimization problems. They basically boil down to finding the maximum or minimum of some function that you have to figure out from context. Okay, so let's do this problem where we have a uh, a spherical cell. Okay, and this cell is going to absorbs nutrients according to the function a of r equals 4/3 pi k1, 4 k1 pi r squared, right? So it's proportional to the surface area here, I think. Okay, so it's absorbing nutrients on the surface area and consuming nutrients according to the function c of r, right? Which is proportional to the volume, right? So once the nutrients are inside the cell, then it can just kind of dissolve them or consume them on whatever processes it needs to. So this is proportional to the volume. Okay, so this is proportional to surface area, and this one is proportional. So this will be k2 times v, which is the volume. Okay, so one of these functions is proportional to surface area, one of them is proportional to the volume. Okay, and our optimization problem, right, is we want to determine the radius of the cell for which the net rate of nutrients, which the net rate of increase of nutrients is largest. Increase of nutrients n of r is largest. Okay, so with these applied optimization problems, you want to first figure out the function that you're trying to optimize and then optimize it, right? So step one is you need to figure out what are we optimizing, right? So based on this context, right, we're trying to determine the radius for which the net rate of increase n of r is biggest. So the function we're trying to optimize is n of r, right? And this net rate would be absorption minus consumption, right? We absorb nutrients into the cell and then we consume them, so the net increase of nutrients that are just kind of sitting in the cell would then be the amount we absorbed minus the amount we consumed. Okay, so our function is this 4k1 pi r squared minus 4/3 pi k2r cubed, right? Where k1 and k2 are just these different rates of increase, the rate of absorption and the rate of consumption. Okay, so we want to optimize this n of r function, right, with respect to r, the radius of the cell. Okay, so we want to find the cell radius that maximizes n of r. Right? We're not looking for a minimum of this function, we're looking for a maximum. Okay, so then step two is we solve for the global max for this function, right? So in solving for a global maximum, we have to look for, so step one of this process would be to look for critical points to find the local max of our function, right? N of r. Okay, so if we look for this, okay, we have n of r is 4k1 pi r squared minus 4 over 3 pi k2 r cubed. All right, so to find a critical point, that's where n prime of r is equal to 0. So we take the derivative with respect to r. When we take the derivative of this with respect to r, we treat 4, k1, and pi as constants. So we get 2 times 4 times k1 pi r. And then we treat k2 as a constant, so this becomes 4 pi over 3 times 3 k2 r squared. Okay, so let's simplify this a bit. We get 8 k1 pi r minus 4 pi k2 r squared. And we want to solve for when the derivative is 0. Okay, because that'll tell us where we have a critical point, which will tell us where our local maximum is. Okay, so we solved this equation. Let's factor some stuff out here. So we have 0 is equal to, let's do a factor of 4 pi r, right? So I factor out 4 pi r from both of these. I'm left with 2k1 minus k2 times r. All right, and then 4 pi r equals 0. So this splits up into two zeros, right? I have 4 pi r is equal to 0, and we have 2k1 minus k2r is equal to 0. This first one gives us r equals 0 as a critical point, and the second one gives us, let's move this to the right, we have 2k1 equals k2r, so that gives us r is equal to 2 k1 over k2. Okay, so these are our critical points. These are our critical points. Okay, we want to find out which ones are the maximum, right? Which is the max. Okay, so let's use the second derivative test, because that I think is the easiest in this case. Let's use the second derivative test. So for point 1, we will check the second derivative at r equals 0. For point 2, we'll check the second derivative at r equals 2k1 over k2. So the first derivative is here, right? It is n prime of r was 8k1 pi r minus 4k2 pi r squared. So if we take another derivative, we get n double prime of r is equal to 8k1 pi. And then here we get minus 4 times 2 times k2 pi r. So that gives us, let's factor out the 4 pi again. Let's factor out 8 pi. 8 pi, then we have k1 minus k2r. Okay, so the second derivative at 0 is going to be 8 pi times k1. And maybe I didn't mention this before, but k1 and k2, right? These are the rate of absorption, rate of consumption. K1 and K2 are both positive, right? They're just positive constants that determine the rate of absorption or consumption. So they're rates, so they're positive, okay? And so that means that the second derivative at 0 is positive, right? Which means n is, or n of r is concave up at r equals 0, which means it has a local minimum there, right? Concave up looks like this. This is a place where the first derivative is 0, so that's where we have our tangent slope being 0. So then that means that it is a local minimum, okay? Let's check the derivative at our second point, right? So 2k1 over k2 is our second critical point, right? So at n double prime of 2k1, k2, we get 8 pi k1 minus k2 times 2k1 over k2. We're left with 8 pi times k1. K2's cancel, so we get minus 2k1. All right, so then no matter what k1 is, this is now minus 8 pi k1. And k1 is some positive number, so this whole thing is negative. Right, so the second derivative is negative, so n of r is concave down at r equals 2k1 over k2, right? So it looks like this, and this is a place where the tangent slope is 0, so we know that we're at the local maximum. Okay, cool. So then, because we have no boundaries for this problem, right? So we were looking for some sort of global max for this function, right? And we basically found that we look at our sign table, f prime, or sorry, this is n, and n prime, and n double prime, and then we'll do r here, right? So at r equals 0, we have first derivative is 0. This is our local min, right? We said it was negative here, sorry, positive here, so it was concave up, which meant it was a local minimum, right? And then at our other point, which is 2k1 over k2, right? We said that was where the first derivative was 0, but the second derivative was negative, right? Which means that this was our local max. Okay. And because the second derivative is negative here, that means that this derivative is decreasing, right? So it's pointing down. So that means that this has an inflection point somewhere in here because it switches from positive to negative, right? And if we were to do this out, if I was to finish this timetable, which I'm not going to get into right now because it'll take too long, but there's basically an inflection point somewhere in here, right? So this is positive, positive, and then it switches to negative, negative, right, at the inflection point, which we won't calculate for now, but we could, right? We'd say, okay, that's that. So then these were increasing, and we know this is a local minimum, which means that we were negative and then positive, right? And then maximum means it was positive and then negative, right? So this was decreasing, and then it was increasing, increasing, and then decreasing again. Okay, so our function is going to look like this for r versus n. So when r is 0, right, n is also 0, right? This is n of r. Every term here has r in it, right? If I look at what n of r is, sorry, n of 0, it's also 0. If I look at n of 2k1 over k2, it's some complicated number, but it's certainly not going to be 0, okay? So if we look at this function, we start at 0. At this critical point, we have 2k1 over k2, right? So this is our minimum, and then it was decreasing from the left, increasing from the right. Wherever this is, n of r star, let's call it, right? So wherever that is, it is a local maximum, so it goes up and then down, right? And then it's decreasing from there. And over here, we can ignore, since cells can't have negative radius, right? So that's unphysical. So then, because it's increasing up to this local maximum and then decreasing from then on, and it's never going to go back up to increasing, we know that this is the global max. Okay, and that's often going to be the case for these sort of applied problems, is even if you're not explicitly given a domain that's bounded, where you're going to be able to check those endpoints, oftentimes there's only one maximum, and everywhere else is decreasing away from it or unphysical. Okay, so this is non-physical on the left. So we can ignore the function there because it doesn't make sense to talk about the nutrient absorption and consumption of a cell with a negative radius because that's absurd. Okay, cool. So I'll stop the video here and then I'll just do another one for the next example. All right.